Okay, so we would now continue the discussion of this VLSI process integration, right? So we have seen the front end of line process where we made the transistors and made, the source, drain, and gate contacts. Now we need to wire up this, so you need to connect these transistors together, and as we have seen in a cross section of the IC on one of the previous slides in the beginning of this module, there are different, multiple layers of metal, right, for connecting these devices together to make circuits. So the first thing, you have these two types of transistors. So this is actually a scheme that is shown. The figure looks slightly different, but it should not matter to you. So what you see here are two gates, okay, and the left hand side thing is a transistor, okay, and then the right hand side thing actually gate is on the STI. So this is something, so typically so far, or let's say so far we have talked about transistors only, but in your integrated circuits you can also have resistors, for example. So one of the way to implement resistors on the IC would be to use polycrystalline silicon, okay, and this is deposited on the STI regions, and then you can actually pattern them into the right shape and size to get the desired resistance. Okay, so that is this kind of device that you see on the right hand side about this yellow region. And of course you have this dark green regions are actually the spacers, and then on the left hand side device you can see the the dark blue or blackish color. That's actually your silicide. Okay, so what you do is the next step is to deposit pre-metal dielectric module. So essentially you would deposit some dielectric layers on top, okay, before you put the metal. Because if you put the metal everywhere, then I have a problem that short circuiting the grasses, right? So first thing is to deposit a thin nitride layer, okay. So it's okay to put it there because now there is no exposed crystalline silicon on top of the wafer. Okay? Everything is covered, right? So you put this pre-metal dielectric by PCVD process, okay, PMD liner it is called. Yeah. Very important thing, beyond this point you can't do high temperature process. Why? Because your silicide is already there. Yeah, so already there is some metal on top of it. So what you find is that you can, for example, if I take nickel monosilicide, NiSi, formed on silicon, source, drain, and the gate, right? If I actually now heat it to high temperature, in the range of 600 degrees centigrade, this would actually react with more silicon, forming NiSi2. But then the contact between that NiSi2 and silicon is not good. Okay, so any process that I use after forming the silicide should not be high. Yeah, you would like to keep it much below 600 degrees centigrade. So all the deposition processes that you're going to do from here on would use, all dielectrics would be deposited by plasma enhanced chemical vapor deposition process, PECVD process, right? And all metals will be deposited by other processes. We'll see that as we go along. Sputtering is one of the most common, but also CVD, and also electroplating. Okay. So now we want a flat surface because we're going to put contact, the metal lines for connecting the devices, right? So you're going to put a high density plasma oxide, okay, which is doped with phosphorus, so it is called phosphosilicate glass. And the idea here is to actually use, you use phosphosilicate glass. It's known to gather impurities, metallic impurities. So the idea is that you provide a sink for the metallic impurities on the, above the transistors. So you already have the nickel, and it has a tendency to diffuse into silicon. So, but now if I put the phosphosilicate glass on top, it tends to actually come into the PSG because of the phosphorus. Okay, so this phosphosilicate glass is known for what is called impurity getter. And then you do this high density plasma oxide, right? So that is, you are actually going to use this deposition sputter process and deposition to sputter ratio. One typical number is given there, 4. But again, as I mentioned, all these numbers could depend on the technology node, and different manufacturing lines may use different processes. Okay, so you get this, it's shown in yellow color, the HDP phosphosilicate glass, right? And then you're going to flatten it out by using CMP. So one thing that you may note here is actually that wherever you have the polysilicon gate, you have a triangular shaped top, okay, in the cross section. Yeah? So that is coming from this thing that we have discussed it already. This is a consequence of the etch and deposition process. You are actually deposit and but also introducing a little bit of sputter etching, right? So that creates this triangular shape. So if you want to review this, you go back to the sputter deposition, or actually even the PCVD process description in a previous module. So you do a CMP of the PSG layer to remove and create a flat surface, okay, wafer surface. So at this point, all the transistors are buried. You don't have any contact to any transistor. Okay, and then so you deposit a very thin layer of oxide, okay, and then you do what is called a contact lithography. Okay, so you're now going to drill some holes to contact your transistors, polysilicon resistors, and so on and so forth. Okay, so this is a scheme where you're trying to contact your source drain but not the gate of the transistor, and then the resistor is also contacted, right? You're going to do this. So you do a lithography, right? And the top layer is actually photoresist. So this is after development of photoresist. Then you're going to etch your liner oxide and the phosphosilicate glass, okay? And the silicon nitride, now you see the role of it. It actually acts as a etch top layer. Why this is important? This is important because if you look at the source drain region, right, you have to etch a fairly thick phosphosilicate glass. But you look on the right hand side, yeah, so that is the etch has to stop on the polysilicon. So that is a shallow region. Yeah? So the now you can see that as you etch, the etch will actually see this. The plasma chemistry would actually see the top of the polysilicon on the right hand side first. But I need to contact the source drain also. So as I continue to etch, so that I etch the phosphosilicate glass till the source drain contacts, the polysilicon top is also seeing this etch chemistry continuously, right? So I should not end up etching the silicide, and then the polysilicon and so on. So it's safer to actually have a layer. For example, in this case, you have a nitride layer, and you can etch your silicon dioxide or phosphosilicate glass with very high selectivity to nitride. So that is the whole idea of putting this silicon nitride there. Okay. Of course, you want to make the contact, right? You're going to put metal to contact your source drain and the polysilicon gate. Okay. So if you have the silicon nitride there, I can't do the contact, right? So I need to etch the nitride liner. Okay. So this should be selected to silicide, but then one good thing here is that I'm going to etch the nitride of same thickness from everywhere. Okay. So I'm going to etch this. I remove the nitride. Now I have this silicide from the top of the polysilicon and the source drain exposed. Okay. So this etch should be selected to silicide, and some regions it may also actually hit the STI, so it should be also selected to STI also. And you remove the photoresist, that's fine. And then you want to put some metal on top, right? So typically you want to remove any dielectric residues on top of the exposed source drain and the gate regions, right? Polysilicon top contact regions. So you do what is called an in situ degas step, essentially to get rid of this dielectric. So you actually do a sputter of the surface using argon, and then you deposit stack of titanium by sputtering, okay, and then titanium nitride. Yeah. So you deposit titanium by sputtering and titanium nitride by CVD. So titanium is a metal, so it gives a good resistance, the low resistance to your silicide, and then you put titanium nitride. So you may ask, what is the role of this titanium nitride? Why don't I just continue with titanium? The good thing about titanium nitride is actually thermally very stable, okay, can stand very high temperatures, and then it's a very good diffusion barrier. So that is a very important thing. Many of this titanium nitride, tantalum nitride, tungsten nitride, these are actually very good diffusion barriers. At the same time, they are actually quite good conductors. Yeah. So that is a very important consideration. So why the diffusion barrier is important? Because you're going to put tungsten, copper, and all the stuff on top for making, to create this wiring between the transistors, right? So the copper should not diffuse into the transistors, right? Source drain regions. So I want to prevent the diffusion of this. So that's why you're going to use a diffusion barrier. Titanium nitride is a very popular diffusion barrier. So now you fill this contact regions using tungsten. So you deposit tungsten everywhere, right? Yeah. So this is shown very nice and clean, right? In the schematic. So you get tungsten. Okay. Then the next step is to CMP the tungsten, right? So you want to chemical mechanical polishing is used for removing the tungsten. So, and then you also remove the titanium nitride barrier from the top oxide cap there, and the pre-metal dielectric. Pre-metal dielectric is phosphosilicate glass, right? Okay. So remove all of this. Okay. So now what you have are all this wiring to the source, drain, metal, meaning gate, wherever you want, are now available on the next layer through the tungsten. So this is called a tungsten plug technology. Yeah, it looks like plug, right? You placed a plug of tungsten, plugs of tungsten to access your transistors. Okay, so that is not sufficient because you have access to various, source, drain, gate, and so on, but you still have not connected them to it. Okay, so you need to put more metal layers on top, right? So you continue like this. You deposit, in this particular case, PCVD silicon carbide layer is deposited. Okay, and then you deposit what is called a black diamond. So this is actually a proprietary technology by a company called Applied Materials, and they use black diamond is nothing but an amorphous carbon film, and the advantage of this is that it has low dielectric constant of 2.2, and also the silicon carbide provides a very dense diffusion barrier. So low dielectric constant is important because all these dielectrics would form part of parasitic capacitors in your chip. Okay. See, when you talked about the VLSI circuits, you considered the delay, right? How fast the circuits can switch, and you always considered capacitive load. So, of course, the gate of the transistor offers capacitance, right? And then you have source, drain, junctions. They also offer capacitance. But all these metal lines running over the isolation oxides would also provide capacitance. Okay, so it's very important that you actually keep this capacitance low, and one way there is to use low dielectric constant dielectrics. So you see these requirements. In the gate dielectric, you want a high capacitance, right? High dielectric constant, because your current, drain current, ID is equal to mu C aux, etc. Right? Now C aux, so the current is directly proportional to the gate oxide capacitance. One way to increase the capacitance is to increase the dielectric constant. Okay, there you need high capacitance. But when you come to the back end of line, you want low capacitance, because all these capacitors are undesirable, but you can't avoid them, because you need to provide isolation between the metal lines. Okay, so here you would really like to use low dielectric constant dielectrics as much as possible. Okay, so there are tricks people use. For example, introduce fluorine into your silicon oxide, so that actually provides a lower dielectric constant. Black diamond, for example. Yeah. Okay, so now in this we'll continue this. So we have this PCVD black diamond and the PCVD oxide deposited on top. Okay, looks like this, right? And then you're going to do lithography. Okay, you're going to do this lithography, and then you're going to etch these layers. Okay, so silicon carbide is used as an etch top layer, and then silicon carbide is opened, and then you do what is called a stripping. Essentially, the top layer is photoresist, right? So you would actually remove that. Okay, and then you are going to do something. Okay, so now what do you have? You have your tungsten plugs exposed, right? And you put some dielectric on top. Okay, so now I am going to put metal on top. Okay, so I would do a pre-clean argon sputtering to remove any oxides that have grown on your tungsten. Okay, and then you put a tantalum nitride, tantalum barrier. Again, you can see this tantalum nitride is deposited. So first you will deposit tantalum, and tantalum nitride is deposited, so that it actually acts as a very good diffusion barrier against copper diffusion into the transistor regions. Yeah, so you're putting multiple layers of diffusion barriers. Very important. Then you deposit copper, thin layer of copper by sputtered deposition. Okay. So apparently it is quite difficult to do CVD of copper. So you deposit a very thin layer, and then you can see that you are going to cover this entire wafer surface using copper. Okay. So you want to grow thick copper by this technique, so you actually would do next is electroplating. Okay. And subsequently you will do a forming gas anneal at fairly low temperature compared to what we have seen for source drain, implant anneals, thermal oxidation, thermal CVD, and so on. Right? So the next step would be the CMP of copper and also the CMP of tantalum nitride and tantalum. So you essentially remove this, okay, on the slides. Again, you got the plug, yeah, but you may actually now recognize that this is really a cross-section view, right? But in the third dimension, so that is actually in the direction perpendicular to the plane of this slide, the copper lines can actually run into this plane. Okay, so it goes deep, and then maybe some other transistors behind this would be connected. Yeah, so we will see that on the next slide. Okay, so you got this copper. Okay. But it is not just like the tungsten plug. So very important thing is that the tungsten plugs were for accessing individual contacts of transistors, resistors, and so on and so forth, right? And the copper is actually connecting them. Okay, though we are showing the cross section, but the copper is also running deep into the plane of this slide. Okay, so you can appreciate it. Now you can use this process. Now you have the copper, right? And then I can continue to do this thing and make multiple layers of metal. And if you look at the top layer, so this actually tells you what I meant by connections using this copper, right? So the copper line is actually running deep into the line perpendicular to the plane of this the cross section that we have seen, and then that can run around and contact various devices. Yeah, source of one device to drain of another one, and things like that. So this scheme actually, this three-dimensional schematic shows 7 levels of metal. Okay, all of them are actually copper. Okay, and then you have of course the tungsten plug and the silicide for making contacts to the transistors. Okay, so this is a real cross section of this transistor that we have seen previously, right? You can here you see only 6, but it's the same thing as what we discussed previously. Okay, so you now understand how you got this, right? This is fair enough. Now we have the transistors are connected together. Okay, so your circuit is ready. Okay, but a chip need connections to the outside world for what? For providing power supply. Right? You need to provide the VDD, power supply. So you have the ground and then the VDD, the voltage that you want to apply. Right, 2 terminals, maybe 3 terminals. Right, if you have a bipolar power supply. And then you need to put in signal lines for communication with other chips and peripherals and so on and so forth. Okay, so you need to now make connections to the outside world. And before that, a very important thing is that you have the metal 6. This is copper. Yeah. So what happens if I actually expose copper to ambient? Has anyone seen this? Some old temples where the roof is covered with copper sheets. Yeah. After a couple of years, it becomes green in color, copper sulfate. Okay. This is not, it looks very beautiful on the roof of a house, but here you don't want the metal to corrode, so it should be protected. Okay, so what you will do is you will actually put some layers on top that would not allow moisture to go in. Very important. Okay, so you can see here this orange thing is the copper, and then you had this silicon carbide, silicon carbon nitride, and then you deposit oxide and nitride. Okay, and then there is a tantalum nitride. So these nitrides are very important because they actually prevent the diffusion of water. So the copper is protected. In the top is aluminum. Okay, aluminum is quite robust because you would actually have naturally one very thin layer of aluminum oxide, which would actually passivate, protect the aluminum. And then you put this wire bonding is done, and that gives you the connections to the package. Okay, so if you look at the package, it looks like this. Right? So you have this wires running to the pins of your IC package. Okay, so you have now your VLSI chips, completely connected, and of course now comes the packaging part, right? So you basically, before you put this wire bonding and so on, so you will take this whole wafer, cut this up into chips. So typically the wafer is about 750 micron or so, a 300 millimeter or 12-inch diameter wafer would be about 750 micrometers. But your transistor and all these metal layers are a few microns at the top. Okay, so you typically thin down the wafer from the bottom. Okay, and then you will place it on adhesive tape, so that when you cut up the chips, they don't actually, get dispersed. So they will stick to this tape. Okay, so you use a laser for cutting these chips, and then you have something. Robots used usually to pick up this individual chips, and they will be placed in packages, and then you make the wire bonding. Yeah, so this can be wire bonding. Typically use gold for gold tungsten. These are used. So gold is used because it gives you very low resistance for the wires, right? And that's good for high performance devices. So one thing you may notice is that if you take this ICs, any of these electronic systems actually become obsolete or may stop working after 10-15 years. So you have to discard this. But there is no problem to discard this. People will come and happily take this. Yeah, or almost all the electronic items. Why? Any thoughts? Okay, so I was reading recently that if you take about 2 tons of electronic waste, you can extract 1 kilogram of gold. 1 kilogram of gold. And the money you need to spend for extracting this gold from the electronic waste is about $2,200 US. Okay, got it? But to mine so much of gold from a gold mine, you need to spend about $40,000 US.